Now I read Modern Approach to Organic Chemistry, written by Dr. J.M. Sehgal. Now I read Chapter 2, Arenes and Aromaticity. Introduction. During the earlier stages of development of organic chemistry, a large number of pleasant smelling organic compounds were isolated from natural resources such as resins, balsams, oil of cloves, and oil of cinnamon. These products comprised a group of compounds whose behavior was found to be quite different from that of aliphatic compounds known at that time and which could not be assigned and any satisfactory structure. As all these compounds possessed pleasant odor, they were termed aromatic. Further examination of these compounds revealed that they were closely related to a hydrocarbon, benzene, which was found to behave typical ring structure involving six carbon atoms. More and more compound gradually more and more compound related to benzene was discovered, but many of them did not have any fragment smell. As such, the term aromatic lost its original significance and is now applied to benzene and all other compounds that resemble benzene in chemical behavior. The characteristics property of aromatic compound that distinguish them from aliphatic compounds are termed as aromatic properties. It may be pointed out, however, that certain compounds that possesses aromatic properties it may be pointed out, however, that certain compounds that possesses aromatic properties do not contain a benzene ring, the typical six-carbon atom ring. However, their structure is basically similar to that of benzene in electronic distribution. This is explained in detail a little later. Therefore, aromatic compounds containing at least one benzene ring are also termed as benzenoids, while other compounds that exhibit aromatic behavior but do not contain a benzene ring are called non-benzenoid aromatic. For example, toluene, naphthalene, aniline, and phenol are benzenoids, while cyclopropenyl cation, cyclopentadienyl, anion, furane, and thiophene are non-benzenoid aromatics. Arenes, as stated above, benzene is the parent aromatic hydrocarbon. In addition to it, therefore, are a large number of other aromatic hydrocarbons which consist of alkyl, alkanyl, or alkaline group linked to benzene ring. In general, aromatic hydrocarbons are also known as arenes. For example, alkyl benzenes, toluene, ethylene, p-hexylene, alkenyl benzenes, styrene, alkyl benzenes, phenyl acetate. Beside the hydrocarbons shown above, aromatic hydrocarbon may also contain two or more benzene rings linked together in different way. For example, naphthalene, anthracene, diphenyl. 2.2 Representation of benzene. The best description of benzene molecules would be in terms of molecular orbital representation, but for most purposes the representation is neither convenient nor very necessary to draw. Therefore, in actual practice, benzene is generally represented as a regular hexagon containing a circle. It is understood that a carbon is present at each corner of the hexagon and a hydrogen is attached to each carbon. The circle denotes the cloud of pi electron. Nomenclature of benzene derivative. The general rules for naming organic compound have been already discussed in earlier classes. We will now consider briefly the nomenclature of derivatives of benzene. However, before processing further, it would be appropriate to present some fundamental points to be made use of during this nomenclature. The carbon atoms of benzene ring are usually numbered from 1 to 6 as shown on the left hand side. However, the numbering can be started from any of the 6 carbon atoms since all of them any exactly equivalent. The typical ring of 6 carbon atoms is present all benzene derivative and is termed as benzene nucleus. An alkyl group or any other aliphatic group such as CH2, Cl, CH2, NH2 attached to the nucleus through a carbon atom is known as side chain. And thus we have side chain nucleus, side chain nucleus. It must be noted, however, that the term side chain is not applied to fundamental group like Cl, OH and NH2 directly attached to the nucleus. 2.3.1 Isomerism in benzene derivative. It has been already studied that benzene forms only one monosubstitution derivative C6H5OH. It can be formed there three isomeric distribution derivatives. These derivatives are known as ortho, meta and para. According to the substituents are attached to adjacent alternate or diagonal carbons atom respectively. In case of tri and higher substitution derivative, the number of possible isomerism product is very small. In such cases, the position of substituent groups are always denoted by mentioning the numbers of carbon atoms on which the substituents are present. 2.3.2 Rule for nomenclature. Now the following are the important rules for assigning systematic names to derivative of benzene. First, the word root for benzene derivative is benzene. Second, in case of mono-substituted benzenes, the name of the substituent group is added as a prefix to the word root. For example, chlorobenzene, nitrobenzene. But in some cases, the name of group is written after the word root. As for example, at the same time, many derivatives of benzene carry special or common names. For instance, third, in case of substituted benzenes, when two similar groups are attached to the benzene ring, the numerical prefix di is added before the name of group and the relative position of the groups are indicated. The suitable number or symbols ortho, meta, para. For example, 1,2-dichlorobenzene, 1,3-dinitrobenzene. Fourth, when two different groups are attached to the benzene ring, the name of both the groups are added to prefix to the word root and their relative position are mentioned. However, if one of the group gives a special name to the compound, then the name of ortho group is prefixed to the special name as shown below. 4-chlorotoluene, 3-nitrophenol. If each of the two group attached to the ring can give a special name to the compound, it is named as a derivative of the group carrying the principal functional group. For example, 3-amino-benzenoic acid, 3-hydroxy-benzonitrile. 2.4 Structure of benzene. The hydrocarbon benzene is the cornerstone of all aromatic compounds. Therefore, it is quite appropriate that we will deal with the structure of this hydrocarbon before discussing the other important aspects of aromatic compounds. The main observation and developments upon which the structure of benzene has been built as follows. First, molecular formula. The molecular formula of benzene as found by analysis and other weight determination is C6H6. Since benzene contains 8 hydrogen atoms less than the corresponding alkane, it should be a highly unsaturated compound. Second, chemical behavior. In spite of its apparently unsaturated nature, benzene behaves in a most remarkable manner in its chemical reaction. Unlike aliphatic unsaturated compounds, the typical reaction of benzene are the substitution reaction and not the addition reaction are illustrated below. A substitution reaction. Benzene readily undergoes a number of characteristic substitution such as halogen, nitration or sulfonation. Fourth, Friedel-Crafts reaction. B. Occurrence of some addition reaction. Under strong condition, benzene undergoes some addition reaction. For example, it can add 3 molecules of hydrogen or halogen under suitable condition. First, addition of hydrogen. Second, addition of halogen. C. Failure to undergo some reaction typical of unsaturated hydrocarbon. Benzene does not undergo some reaction characteristic of aliphatic unsaturated hydrocarbon. For example, It does not dechlorize potassium permanganate solution. It does not undergoes addition of halogen acids. Third, isomer numbers benzene yield one and one type of monosubstitution product C6H5Y. For example, only one bromobenzene and only one nitrobenzene are known as exist. This fact clearly indicates that all the six hydrogen atoms of benzene are equivalent to one another. The disubstitution product of benzene C6H4Y2 or C6H4YZ can exist in three isomeric forms, that is the ortho, meta and para forms. Thus only three dichlorobenzenes C6H4Cl and other three bromophenols C6H4BROH have been obtained. The knowledge of isomers numbers of substituted benzene provide extremely useful in testing the validity of various possible structure for benzene. For calculus structure, theoretical there would be a number of possible open chain structure for benzene, but none of these can explain as to why benzene undergoes substitution reaction for more readily than addition reaction, and none of these can justify the isomer number of substituted benzene.